Hello everyone and welcome to Digital Elevation Models and Application course, and this is the 18th lecture in which we are going to discuss how digital elevation models can be used for estimation of solar and wind energy potentials. This is very important derivatives one can have using digital elevation models. So these in these two energy sources, solar and wind, how these we can employ, we will be discussing very briefly here. As we know that the sun solar radiation that may reach to the earth surface directly or maybe through diffuse radiation and maybe through the reflected radiation. So if this is the location on the surface of the earth, then the radiation can reach through three ways. That is the direct radiation, diffuse radiation and reflected radiation. And also they say we use the word insolation for the incoming solar radiation. So whatever the radiation which is coming through whatever the source is all combined in form of insolation. So we call as incoming solar radiation or insolation that originate from the sun, and as we know that it gets modified while it is travel through the atmosphere, because between the earth's surface and the sun there is a atmosphere which modifies this solar radiation to some extent, but even then a large amount of solar radiation reaches to the earth's surface. And this insulation may also get modified because of topography and surface features. Topography in a hilly terrain, insulation is completely different than in a flat areas like Indo-Gangetic Plain, and also surface features like maybe vegetation, forest, water bodies and so on. And also it might get intercepted at the earth's surface as direct, diffuse or reflected components. So but the estimations which we are going to make about solar radiation or for solar energy may combine the entire complete insulation, that all three components. So as we know that direct radiation is intercepted unimpeded in a direct line from the sun, that is the direct sunlight where is reaching, direct solar radiation will reach. Diffuse is scattered by atmosphere constituents, maybe such as clouds or dust or other materials which are present in the atmosphere. Some gases can also diffuse the radiation, whereas reflected radiation is from the surface features, and especially this reflected radiation we get in a hilly terrain or areas which are having taller buildings. Their reflected radiation component is much more in insulation, and the sum of this direct, diffuse and reflected radiation, as I have been saying, is, or we can call as a global solar radiation or total, basically total solar radiation. And generally the direct radiation is the largest component of total radiation. Diffuse radiation is the second largest component, and the third one, which is the reflected one, will have the very little in that sense. So reflected radiation generally constitutes only a small proportion of the total radiation which is reaching to the earth, except for locations surrounded by highly reflective surfaces such as snow cover. And you know that the snow cover areas where you are having glaciers or fresh snow, the solar radiation because of reflection is very high, and therefore people wear goggles to reduce that radiation reaching to their eyes, otherwise it is very harmful. So generally this solar radiation calculations can be done on a GIS platform. The main input is going to be again a digital elevation model, but what it will calculate, not all three components but only the total radiation component will be calculated, and therefore the total radiation is as we have discussed, is the sum of all three components. Solar radiation can be calculated for a point location or for a entire given digital elevation model or area. Now there are 4 steps which involves while calculating solar radiation based on a digital elevation model, and that is the calculation of an upward looking hemispherical view set based on topography. So far we have not discussed the typical view set analysis which is based on digital elevation model, but this view set which is used in case of solar radiation is little different. That is only upward one. The view set analysis which we will be discussing in future lectures is not really upward but looking along the horizon. So there are 2 different kinds of view set. One is for solar radiation looking upward, another one is looking along the horizon. So in the first step is the calculation of upward looking hemispherical view set based on the topography. Basically what does it mean here is the how much sky is available to us, because that will allow us to understand how much solar radiation will reach. So if I am in a valley in a hilly terrain, then the sky which is available to us is a very small. If you know the sky plot in case of a global positioning system or these navigation systems, so if we are in the valley, our sky plot will have these satellites only along a line or along a valley, and therefore our signals reduces. Same thing here, that this hemispherical view set will be very restricted if I am in a valley. But if I am on a mountain top, then the entire sky is available for solar radiation to reach to that point. So therefore this view set analysis, hemispherical upward looking view set step is very much important towards the solar radiation analysis. The second one is the overlaying this view set on a direct sun map to estimate the direct radiation. So this sun map can also be calculated using digital elevation models. Then overlaying of this view set on a diffuse sky map to estimate diffuse radiation. And the fourth step is repeating the process for every location of interest to produce an insolation map. And I will show you some example. As we know that since radiation can be greatly affected by topography, especially this is hilly terrain versus plain areas, and some surface features, maybe vegetation, maybe snow cover and ice, glaciers. So the key component of calculation of algorithm requires the generation of an upward looking hemispherical view set. That is the first step for every location in a digital elevation model. So that is done. This hemispherical view set are similar to upward looking hemispherical or a fish eye photograph, which view the entire sky from the ground upward, similar to the view on a planetarium. And this is what is mean by this hemispherical view set. If we are having some trees in the surroundings, then this view set is going to be little restricted. If we are having mountains in the surrounding or some hills, then again this view set will be restricted. But if I am in a completely flat area where no ground features are present, like in a desert area, like in Rajasthan or in the Bikaner area, we may get a complete free or a 360 degree complete circle of view set upward, which will not have any destructions from mountains or hillocks or vegetation. So an upward looking hemispherical, this photograph, the fish eye kind of thing, providing a view of visible sky and the sky directions obstructed by the surrounding topography and surface feature. Because this is how it will restrict the energy to reach to that particular point, which is in the center. And this is similar to the view as we have seen looking in case of fish eye. This is how a eye of a fish looks the outside world. The amount of visible sky plays an important role in the insolation at a location, and that will come, of course, through this view set analysis. So upward looking hemispherical view set can also be useful to plan GPS campaign in a hilly region, as I have given the example earlier. For example, a sensor located in an open field has higher insolation than a sensor located in deep canyon. And ViewShed is a raster representation, because we are using a digital elevation model, which is a raster model, and of the entire sky that is visible or obstructed when viewed from a particular location, and looking upward. So this ViewShed is calculated by searching a specified number of directions around a location of interest and determining the maximum angle of sky obstructions or horizon angle. And for all other unsearched directions, horizon's angles are interpolated. And likewise, we calculate the ViewShed. These horizon angles are then converted to a hemispherical coordinate system, because this is not a planar coordinate system, and thus representing a three-dimensional hemisphere of directions as a two-dimensional raster image. So this much calculation is required, and each raster cell of ViewShed is assigned a value that correspond to whether the sky direction is visible or obstructed. And output cell locations, because ultimately we are going to have in form of rasters, so row and columns correspond to zenith angle theta, and that is the angle relative to straight upward, and azimuth angle, that is the angle relative to north on the hemisphere of the direction. So along the perimeter we have the azimuth angle, and from perimeter towards the center we will have the zenith angle. So these two angles are important. Here is the example, like this is our digital elevation model. So different directions will have different values or azimuth here, and if I take the same ViewShed example or fisheye lens example, then this is the area or the sky which is open at this location. So the calculation of ViewShed for that particular cell would be involving that horizon angles are calculated along a specified number of directions used to create a hemispherical representation of the sky, and the resultant ViewShed directions, whether sky directions are visible as shown here in the white color or obstructed as shown in the gray color. And the ViewShed is shown here is overlaid over a hemispherical photograph to demonstrate this theory. So next step is calculation of sun map, and that is the direct solar radiation originating from each of sky direction is calculated using a sun map in the same hemispherical projection as ViewShed, because for each location the upward looking hemispherical calculation has to be done. So it will be the different projection system, but ultimately it has to be projected in a planar form. And sun map is a raster again representation, and that displays the sun track or apparent position of the sun as it varies through the hours of the day and through the days of the year. So season to season is changed. All these parameters will be incorporated while calculating the sun map for a particular location. And this is again the analogy here. It is similar to while looking up and watching the sun's position moves across the sky over a period of time. So if I am located in a place and look upward, then I can see how the sun from where it appears and where it disappears. And so this sun map calculation will incorporate those informations. Sun map consists of discrete sun map sectors, which will be see through quickly through an example, which are defined by the sun's position at a particular interval during the day, that is maybe hours, and time of the year, that is days and months, because in season to season is change, but a day of the hour of the day, in the morning it is different, in the evening it is different, and in the noon it is different. And the sun track is calculated based on the latitude of the study area and the time configuration that defines sun map sectors. And for each sun map sector, we will see in a diagram that these sun map sectors are unique identification values is specified along with its centroid, zenith and azimuth angle. And the solar radiation originates from each sector is calculated separately, and then the next step is overlaying over the view set so that we know that where it will reach and where it will not reach. And likewise, this is a typical sun map. One example is shown here for when solar winter solstice is on 21st December and summer solstice on June 21st at latitude at 45 degree. So when this scenario is there, then each sector is representing the time of that particular day, and also along the perimeter you can see the months how they vary. So between December after 21st, so you are having 22nd December up to 22nd June, this sun map has been calculated in different sectors. So each sector is representing different time of the day of the sun position as a month changes. So say if I take the example here, then in April these sun sectors is quite large, whereas in month of December the sun map in the or the sectors in sun map are very small. So likewise we know that how much time the sun is going to be there over a part of the earth at a particular latitude. So it will of course change latitude to latitude. As we know, in the polar regions, in higher latitudes, sun may remain in summer time for 6 months, and in winter time in northern pole in winter time may not be any sun. But in this mid latitude regions like 45 degree and so, this is the scenario which we get here. So as mentioned earlier, that the sun sector, which has different color shown here, represents the sun position using 1.5 hour intervals. And so you are seeing these sectors, this is like 15 hours, this is 14 hours. So there for each half an hour there is one sector through the day and monthly intervals through the year. These months are shown here. And this image, that is sun map, is in the same hemispherical projection as we have this view set, and therefore this overlaying is possible. So the position of the sun is represented as it moves across the sky during the time of the day and time of the year. Now in this sky map calculation that we will be overlaying this example, but this diffuse radiation has to be also incorporated. That diffuse radiation originates from all sky directions as a result of a scattering by atmospheric components, cloud particles and so on. And to calculate diffuse radiation for a particular location, a sky map is created to represent a hemispherical view of the entire sky, divided in a series of sky sectors defined by zenith and azimuth angles, which we have already discussed. And each then sector is assigned a unique identifier value along with the centroid, zenith, azimuth angle, and this diffuse radiation is calculated for each sector based on the direction, that is zenith and azimuth. And likewise here that is sky map is calculated, and in which with the sky sectors defined by here 8 zeniths. So zenith as mentioned here are coming from this perimeter or outer the circle to the inside, and 16 azimuth divisions are there. 16 azimuth divisions are there. North, major ones are north, south and east, west, and then you are having different. So when you are looking upward, then these directions for east, west would change. That is why there are different directions. So these are the 16 azimuth divisions, and these are the 8 zenith divisions are there. And again, remember, this is again upward looking hemispherical projection. So each color represents here is a sky sector or portion of the sky from which the diffuse radiation originates. So this is so three parameters in order to calculate the total insolation, total radiation we have discussed. Now it's a overlaying time. So overlaying the view set with sun map and sky map, and during the insolation calculation, the view set raster is overlaid with the sun map and sky raster to calculate diffuse and direct radiation received from sky direction. So both types of radiation, diffuse and direct radiation, have come here. Reflected radiation, if we want to incorporate, will require the ground feature information. So that means a land use map has to be there. So in this discussion, we have not included that the reflected radiation, but two major, because they are the major components towards the total solar radiation, have been incorporated. So the proportion of visible sky area in each sector is calculated by dividing the number of unobstructed cells by the total number of cells in each sector during this overlay process, and this allowance is made for partially obstructed sky sector. And this is how you get the result. When we apply this sky map and sun map, this is what the scenario we get. And again this masking is done, that is overlaying is done in this example. So this becomes our sky map. So the overlay of a view set on a sun map and a sky map, and this of course this is the obstruction which we are seeing in this particular example because of the topographic features which are present, maybe hillock or hills, mountains, and maybe some trees and other things. And the solar radiation is finally calculated by summing direct and diffuse insolation which is originating from the unobstructed sky directions. And likewise you get the complete information of total solar radiation minus reflected radiation is calculated. So we know at what location how much solar radiation will reach. However, as mentioned that for each location such calculation has to be done. So when you are performing such analysis on a GIS platform using a digital elevation model, it requires lot of time to calculate, because for each location, or for rather each cell, this has to be calculated. So it requires lot of time or computation time on a GIS platform for total solar radiation. What are the applications of this solar radiation analysis? As we know that insolation, that is incoming solar radiation, is a driving force of the Earth's physical and biological systems, and knowledge of amount of insolation reaching at a specific geographic location is definitely helpful for application of diverse field and such as landscape ecology, meteorology, environmental modeling, agriculture, and of course finally a very important one is the solar energy generation estimation. Before investment is made, before a solar power plant is constructed at a location, one would like to know how much insolation or total incoming solar radiation would be available at that location. And this estimation can be done very easily implying a digital elevation model of that area. Of course, one other advantage, because we calculate the sky map here, so in GPS campaign planning, especially for hilly region, this sky map can also be used. So if I know in which area I am going to work, suppose I am going to work in a valley, so I know what is the sky map or open sky is going to be available. So obstruction versus open sky, that can also be calculated. Also the applications of under this applications of solar radiation analysis, the knowledge of how much sun an area receives over a period of time may be useful in determining a new site for a ski resort or a best location for growing, especially crop where specific microclimatic conditions are needed for optimal growth. This solar radiation information can also be used indirectly or directly related with the weathering studies or weathering processes which are related with erosion as well. So in another example, the insolation maps have proven important for predicting the behavior of forest fires and making decisions concerns the best firefighting methods, because of the heat involved and the radiation which will the areas which are receiving maximum radiation may be prone from forest fire point of view. For civil engineering and urban planning, insulation can be an important input for suitability models used to determine optimum sites. In the colder areas or the climate is colder, then solar insulation can be helpful to reduce the heating budget of a building or a house, whereas in hot climatic regions like in India, then this insulation information can again be helpful to find out that which direction would be the best for windows and other open areas. So likewise, a lot of applications are there which can be used. And as mentioned that for it has to be calculated for each location, so that location have to be selected. Like in this example, 4 locations have been selected, but if we submit for entire area, it takes a hell of time. So one can start with this, that if these are the sites for vineyards, potential sites for vineyard, so 4 locations are shown over a shaded relief model which is derived from digital elevation model, and then maximize the crop growth. It must be determined which location will have the maximum amount of sun exposure during the growing season, say April to October. So a comparative study can be done very easily, and this analysis shows that these red areas where the solar insolation is going to be high, and especially the site which is marked as 3, and the 2 will have less, whereas the 1 will have the minimum. So using this area solar radiation analysis, the global insolation, that is direct plus diffuse radiation, can be calculated for an area showing where the highest amounts of radiation are during the summer months. So if you are having some specific requirements, you know the window, time window, and the area window, then for that specific area, things can be calculated as shown in this particular example, where a time window was also given about the summer months. So global insolation calculation for each site can be located, as we have seen that the location 3 is the best in this region. Also some statistics can also be derived from the attribute table of that one, and more precise analysis can also be done while involving a higher spatial resolution data and some other inputs there. Now another part of this presentation or this discussion is how to use digital elevation models in wind energy. Because if it is flat areas, the wind may have the same intensity and same direction throughout. But if it is a hilly terrain and still we are targeting some sites for wind energy, then we can employ a digital elevation model to find out the best sites, locations to generate or these wind plants. So how we can use the digital elevation models? So basically large area screening has to be done with the existing data. So large area screening usually begins with a review of estimated wind resource maps of that particular area and other data, that is especially meteorological data, informations, pressure, temperature, and of course wind speed, wind directions. And then ultimately then comes the, apart from this weather and climatic data, then comes the terrain data, land use data, land cover data, and other accessibilities or logistic data as well, and availability of grade and other things. So here the contribution through digital elevation models towards the estimation of wind energy is going to come only through terrain data, that is from digital elevation model. If I take the example of India, then these are the areas where we are having very high potential of generation of wind energy because of open areas and less undulations and other things, no vegetation, not much. So this is the wind power density map at 50 meter AGI, and these are the areas which are most suitable. Then you are having some other areas. Some areas are not suitable, and this is wind power density map also for different states is there, and this wind power density map of India at 50 meter level is also given here. For different locations can be estimated, and these are the, for example, one example is given here that these are the wind turbines have been located where one can get the best benefit of wind in a hilly terrain, and that example is given here, which is again has been analyzed based on this digital elevation model, which is shown here in form of a shader relief model, and that best suitable locations. So as you can see here, the edges, this escarpment has been found most suitable for wind energy point of view, or these sites which are most suitable, and some other points are also there, but the valley part is not suitable. So here you will have the maximum wind in this particular example. So employing a digital elevation model or shader relief model, incorporating other parameters, one can locate or find a most suitable sites for wind energy. Wind climatology in India is influenced by strong monsoon circulations. So we are having these informations available. Probably the information which has been missing so far is the topography. How topography is influencing, that can also be incorporated. And we know that the southwest monsoon during May to September brings the best winds. Wind speed during November to March is low, except in southern tip of Tamil Nadu, and west wind sites are in Kerala, Karnataka, Tamil Nadu, Gujarat, Andhra Pradesh and Maharashtra. These are the areas which are very open and less forest covers, and open very close sometimes to the sea, and therefore they are having quite good potential for wind energy generation. So this brings to the end of this discussion. Thank you very much.